Hello, this is the next video in a playlist that I'm calling General Linear Models, Design of Experiments. And within this larger playlist, we're creating little mini-series, and each mini-series deals with a different type of experimental design. And here, this mini-series, we're dealing with analysis of covariance. This is actually part 9 of a 9-part mini-series, and the second R illustration we're doing of analysis of covariance. So in this video, we're going to look at a two-factor ANOVA with two covariates and no interaction. So the example is from Ronald Christensen's book, and I actually don't remember what the data represents, but let's load it and look at it. So Y is our response variable. A and B deal with treatments, and X1 and X2 are covariates that we think are associated with the Y vector. And then what we're going to do here is go through each part, so part 1 through I think part 5 or 6, illustrating what we developed theoretically and show how it translates to the R program. So part 1 deals with model development. So here currently our data is in a data frame called Ronald, and that's for Dr. Ronald Christensen because it came from his book. And so we'll put the Y in a variable called Y. The Z's, which are the two covariates, and they're centered, so we subtract the mean off of each of those into a variable called Z. XA deals with the part of the design matrix dealing with treatment A, and then XB is the design matrix for the B treatment. A treatment has 4 levels, treatment B has 5 levels. Then we need a column of ones that deals with the mu parameter in the ANOVA design. So X, which in our part 1 we associated with the ANOVA part of the design. So if you've watched any of the previous little mini series in this playlist on design of experiments, this will be very, very familiar with you. Now, if we add in the 2 columns for the covariates, we're going to call that X dot F, and F stands for full model. So this is the full design matrix. Now, in part 2, we looked at the different types of column spaces associated with this design matrix. And we need to create perpendicular projection matrices for this design matrix. And we're going to create M dot F, which is the perpendicular projection matrix onto the full column space of X. MZ is the perpendicular projection matrix on the column space of Z. MA is the perpendicular projection matrix on the column space of A for the treatment A. MB, perpendicular projection matrix onto the column space associated with treatment B. J is the perpendicular projection matrix associated to the vector of all ones. M is the perpendicular projection matrix on the column space of X. Now X, remember, that deals with only the ANOVA part of the model. And in a previous video, we showed that M is, so we could do X transpose X, generalized inverse X transpose. But we showed it has a structure of M dot A plus M dot B minus J. So we're just going to kind of cheat and do it that way. The next statement, I show that they're equal. So M is the shortcut way, but here we take X transpose X, generalized inverse X transpose, and we use the function all equal to show that they're all equal, and they are. So the identity matrix, it's a 20 by 20 identity matrix. Capital I is a reserved function in R, so we call it ID. Now these next column, or these next perpendicular projection matrices kind of have a weird naming convention, but if you were to watch part 2, I think it would make more sense. So this first one deals with the column space of I minus MA times Z. And there we added a well-chosen zero to the model, and then manipulated it, created a design matrix where it has orthogonal subspaces, and it helped us develop a structure when calculating the least squares estimates. So that's what this deals with. M1BZ, that means the part associated with A is removed. So it's the column of ones, column space associated with treatment B, and the column space of the covariates. And we look at that perpendicular projection matrix. M.1AZ means column space associated with treatment B has been removed. And we'll need that. We'll need those pieces when we do the partial F test. Now let's derive the least squares estimates for these parameters. Now the beta parameters are associated with the ANOVA part of the design. Gamma parameters associated with the covariates. So let's solve for the gamma vectors. And since the Z matrix is full column ranks, then we can calculate a unique estimate for the gamma parameter. So this is 2.09 is associated with the first gamma parameter, or the first covariate. 0.39 is associated with the second one. Now, to me, this section I find so darn fascinating, and you'll see why in a second. Now, these are absolutely unique estimates, and according to the theory, since it's full column rank, they are. Now, this is a side note. Now, Ronald was the data frame of that holds our data. So let's just do a linear, linear regression, multiple linear regression of y, x1, x2, a, and b. And so this is, it's just a standard linear regression. But what I wanted to show you is the estimates of the parameters. Look at this, 2.0961, 2.0961. Here's this one, 0.392. They're uniquely estimable. Doesn't matter what method we use. They're uniquely estimable. And that's just kind of crazy right there. But then what I'm getting ready to show you is even more crazy. So here we load a library, PRA, CMA, and that has a function called null space, which I like because it helps me grab vectors that are in the null space so I can add them to a generalized inverse, creating different generalized inverse. So let's look at this temp, and it creates two vectors that are in the null space. So now when I create a generalized inverse using the full column design matrix, so it's x.f. And so it's x.f transpose x.f. That's the first generalized inverse. So now this next command, I make sure that it's a generalized inverse. So I take x transpose x times generalized inverse x transpose x, and it should equal x transpose x. So let's see. And it is true. They're 100% equal. Now generalized GI2, generalized inverse 2, I just add the first column of the null space to every column in GI1, and it creates different generalized inverse matrices. First, let's see if it's generalized inverse matrix, and it is. Now I create a third generalized inverse matrix, and let's see if it is a generalized inverse matrix, and it is. And they're all different. They're all absolutely different. So now let's create least squares estimates of our beta parameter. And it's kind of weird, like beta stars, this beta parameter is associated with all the parameters, so even the gammas. And so perhaps my notation in this program is not good. But in the first one, I use the generalized inverse GI1, and I create these. This is it. This is least squares estimate for beta parameter, for the beta parameter. Oh, notice this though. This is what I find cool. These last two are associated with the gamma parameters, and they're 100% same as what we calculated earlier. Now let's look at a second least squares estimate, and this is 100% a least squares estimate of the beta parameter. But notice the last two are the same. Here's a third estimate, different from the previous two. Notice these last two, 100% the same. So let's do them side by side. Look at these. All three of these vectors are 100% least squares estimates of that beta parameters for the full model. And notice the last two parameters are uniquely estimable. And the theory tells us that. And I'll reprint the gamma tilde just to show you that it is the same. To me, that's just mind-boggling. It's so cool. So now, even though the least squares estimates for the beta is not unique, if we pre-multiply it by x, the design matrix, Boom, it is unique. And let's look at that. So we take at least the first one, the second least squares estimate, and the third least squares estimate, pre-multiply it by x, and they're 100% the same. To me, that's just so fascinating. So now let's look at the sum of squares and the f-test. So let's look at the full model here, and notice that all these little sums of squares are a little bit different, right? A is 65 here, A is 57. That's because the column spaces are not orthogonalizable, if that's a word. But the residual's the same, right? The fitted model is unique. And so the residuals, which is what's left over after you use the fitted model, is the same. And to calculate the residual, the sum of squares residual, or sum of squares error, it's always I minus m, and where m is a perpendicular projection matrix on that column space. So it's y transpose, I minus m, y transpose, and we better get 8857, and we do. The degrees of freedom is always the rank of that quadratic matrix, which is 10, so that's the same. Now, here, let's conduct the sum of squares for treatment A. So what that means is we're going to create a model where we drop the treatment A from it. We're going to grab this sum squared error, compare it with the sum of squares with the full model, take that difference, and actually this is what ANOVA does. So ANOVA mod 2 takes the sum of squares from this reduced model, sum of squares from the full model, subtracts them, and we get 57.52. The degrees of freedom, well, let's see if we get this to here. Yep, 57, it's the same. And so this sum of squared error is, it's the perpendicular projection of the full model minus the perpendicular projection matrix onto this reduced model. So it's 1BZ because A has been removed. Now the degrees of freedom is associated with the rank of that quadratic matrix, which is 3 and 3. And I don't know why I print that again, but I do. Oh, 8857. Now sum of squares treatment, sum of squares for treatment B means we fit a model without B in it. Then we compare the sum of squared errors for the full model and then this reduced model. Oh, so here's the full model, 8857. This reduced model, 183. The difference is 94. So to calculate it from scratch, we take the perpendicular projection of the full model minus the perpendicular projection of that reduced model, and that's y transpose y, and we get 9471. It's the same. Degrees of freedom is the rank of that quadratic matrix, which is 3. And that's it. So here we look at a test or the sum of squares associated with Z. So we fit a model without the covariates, and we look at the differences. So this is the difference of the full model and the reduced model. That difference is 138. So to calculate it from scratch, that's a perpendicular projection matrix, the full model. M is a perpendicular projection matrix onto the ANOVA design part of it. That is 138.33, so it's the same. Degrees of freedom is the rank of that quadratic matrix, which is 2, and that equals 2. Now, I'm going to reprint out the summary for the full model. Let's look at the mean squared error. So that's the sum of squared error divided by its degrees of freedom. Mean squared error, 8.86, which is what we have here. Mean square residual, mean squared error. Mean square treatment, of course, sum of squares treatment divided by its degrees of freedom, and we get 1917, which is the same. The f-test is the ratio of those mean squared errors, which is 2.165, and that's the same. P-value is the area in the tail, and it's 0.15539, and that's the same. Right? Now let's do the this is a good point. So look at the order of these. I do A last, right? Because then this is a type 1 sum of squares, so it's actually adjusted for everything before it. And that's what we want. So now this next one, I have to run summary of mod 1, where we put B last. And then this is the sum of squares that we're interested in because it's adjusting for everything else. So then we calculate the mean square treatment, 2368. The F test is the ratio of the mean squared error and the mean square treatment B, 2.67. It's the same. The p-value is the area in the tail, 0.09. It's the same. Now, estimability, and actually this kind of ended up a little funky on the screen. I put gaps between it to show you that this is associated with mu. This is associated with treatment A. This is treatment B. And then these two are the covariates. And what I wanted to show you here is that the individual estimates for the parameters are not uniquely estimable. Now the covariates are the parameters for the covariates. So this is for tau 1. Oh, and in this little 4-part mini-series on estimability, and actually part 4 of that mini-series, there's an amazing theorem that gives us a full proof to show something is estimable. If we take that linear combination times this, which is x transpose x, generalized inverse, x transpose x, and we get this linear combination back, then it's estimable. And if we look at this, this doesn't look like this vector of all zeros with the 1. So it's not estimable. Same way here. So the first beta parameter is not estimable. But these linear combinations are. So this is a linear combination. This is just picking off the first gamma parameter. And when we run it through this theorem, right, we get it back. Now let's look at here. This is a linear combination of mu, tau 1, and beta 2. Let's see if that's estimable. And it is, because we get it back. And then we can put in the first gamma parameter and we get it back, so it's estimable. Actually, all these are estimable. We get them back. Now, the one I just ran is actually a treatment contrast. That's cool. And this one here is a treatment contrast for treatment B. This is a treatment contrast for treatment B, but adding in the effects of the covariates. And this is just a crazy combination that I, just for fun. Now, one thing I did want to show that, estimability means it's a unique estimate. We get a unique value. So that means linear combinations of any least squares estimate of the beta parameters should be the same. So notice that these 3 linear combinations are 100% the same, but we're using different least squares estimates. So all these are different, but the linear combination is the same and creates an estimable function that we determined up here. So all 3 of these values should give the same value, and they do. Same way for the others, these are all estimable, so we get the same value. Now the variance associated with these estimates, I'm going to just pass you off to that theorem in part, I think, 2 or 4, where we divide the variances of these estimable functions. Now theorem 1 in this little mini series says if it's estimable, then it has to equal this value here. It has to be part of the row space of I minus mzx. And I'm going to let you go to that video to see it. But when we multiply it times this, notice that we get our vector back. So this is 100% the same as this, right? We get it back, and that's what the theorem said. And actually we use this theorem to prove theorem 2 that says if it's a linear combination of the parameters associated with a treatment and it's estimable, then it has to be a treatment contrast. So here we create 2 little treatment contrasts, and we get it back. Now this one, this is not a treatment contrast, so we shouldn't get so we don't get the linear combination back. So we know it's not estimable. Now we start this library at EM means, which is estimated marginal means, and let's create two little treatment contrasts. So this one is a contrast for treatment A, and this is a contrast for treatment B. And let's run these through the estimated means. So the first one, A, we create a treatment contrast, this one here specifically. Now if we were to calculate that by hand, we just take the linear combinations times that least squares estimate. And notice, no matter what least squares estimate I get, it's the same. It's 8.78. Now the standard error associated with it is the square root of the variance, which is what we calculated up there. And it's 100% the same. So we're calculating it by scratch. We're using this estimated mean margin. So here treatment contrast for B, right? And now to do that, we take that linear combination times the least squares estimate for beta, and it should be the same, negative 5.37 for no matter what least squares estimate we use. And the variance associated with it is square root of the variance. That's the standard error, 5.7, 5.7. It's the same. So this is all we have for today, and it's kind of exciting how it all just works out. Now I'm going to try to remember and copy and paste this code into the comments. If I don't, I'm hoping you comment and tell me to do it, because then I'll 100% do it. I want to share it. This is all I have for this video. Hopefully you enjoyed that. I sure did. Now the next mini series we do are what's going to be called factorial designs, and that'll be coming in a week or two. Hope you enjoyed it. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.